Taylor rule is a relationship that sets out the interaction of monetary policy and target variables. And up to the early 1990s, a large part of monetary policy was discussed in terms of targeting monetary aggregates and money supply. Taylor made the observation that the Fed funds rate may be the policy instrument, and that if we take this as a summary of what subsequently came to be known as the Taylor rule, in effect we have the Fed funds rate, so the policy instrument, should be equal to inflation plus 0.5 times an output gap plus 0.5 times an inflation gap, where P again is inflation minus a policy target of 2, and then 2 is a kind of equilibrium interest rate, where when other things are in balance. So Taylor posited this as being a compendium, sort of a relationship that comprised observations on the implementation of the Fed funds rate, or the implementation of monetary policy during the early Greenspan period. And if we look at how the Taylor rule or policy rule was, the prism through which the policy rule was looked at, he compared the actual Fed funds, so this would have been during the Greenspan period, and that's the bold line, and then the broken line would have been the policy rate, which was the Taylor rule or policy rule. Okay, so question then arises, how do we implement empirically a Taylor rule, and also how do we estimate the Taylor rule? Obviously of importance here is the output gap, and the output gap estimation in the Taylor rule, in what was originally proposed from the Taylor rule, the output gap was the level of real GDP minus a trend which John B. Taylor took to be equal to about 2.2% per year, and divide by the trend. So if you like, the lowercase y denoted, which was the input here in the Taylor rule, denoted the GDP growth minus or GDP level minus the trend divided by the trend. Different implementations of this are possible. Right? So one implementation here will concentrate or focus on growth rates, and to obtain data for the growth gap or the output gap, I will look at the FRED database, economic database, provided by the Federal Reserve of St. Louis. So let's remove this for a second, and let's have a look at data, obtain data from the Federal Reserve of St. Louis, so FRED database. And let's click through, and we're looking primarily, well, for Taylor rule, we're looking for consumer price index data, inflation data, and real GDP for the moment. We'll focus on real GDP. And we'll look at this series. It goes back, it dates back to 1947, 01, 01, and runs all the way to 2015, 401. So if we take a look at the data here, description, real GDP, domestic product, 3 decimals, billions of chained $2009 seasonally adjusted annual rate. So we have a real gross domestic product series. It's quarterly. We don't generally get higher frequency for GDP, although for industrial production, which I've looked at in another video clip on YouTube, industrial production is monthly. So let's download this data. Let's open the data up. And the data appears. We'll enable editing. So it's being directly downloaded from Federal Reserve St. Louis, stretching back to 1947 and going up to 2015. Now we want to estimate what was the historic growth rate. So in a sense, what we would like is to construct some kind of trend and compare that trend to actual growth. So the technique I'm going to use here will involve using an exponential regression. And we can have a look at that perhaps using exponential regression using a linear model. So, and if we come down, we'll try this one, exponential regression using a linear model. And what we have here is, let's say we have a particular series and we expect that it'll grow over time. This might be analogous to money earned or the future value of a sum of money where the interest rate is continuously compounded. Here we're thinking in terms of the level of GDP, and we can think of the original value or the initial value, and then we can think of the beta here as a measure of growth, and x as perhaps the time period. If we take the natural logarithm of both sides, then this breaks down using properties of natural logarithms. Natural logarithm of y would be equal to natural logarithm of alpha plus beta x. And so herein then lies, if you like, the rationale, right, for taking natural logarithms. So let's have a look at that in terms of its implementation. So if we close down this window and we say let's take the natural logarithm of, okay, so this series is this series here would be GDP, and following in line with this C96, and we're taking the natural logarithm of that. So same again, copy and just paste in, and just to be clear, we'll put ln brackets around, close the parentheses, that's equal to natural logarithm, and we take this value, close the parentheses, and then pull the value down, and you'll notice that we have quite a few values of the order of 287. So that's quite a few. Now, next, following in line, going back to our guide here, we need to take, we're regressing, if you like, the natural logarithm of GDP on some constant, and then this beta, if you like, is the growth rate, and t is the magnitude of increase. And in a time decay or time growth type linear model, x here would denote the time period. So if we put this down for a second, we could say, let's take time, and let's take the first observation as 0 and pull down. We could think of this as quarters. And I didn't see that properly. It should be 0, 1, and then drag down. And we should have 287 minus 1, or 273. Yeah, 273, because the first couple of cells here, 12 or so, are not counted. Okay, so we have time, and then to estimate. So if we're estimating a regression, so let's take this again. If we were taking this particular model, let's see if we can copy that somehow. No. Okay, if we took that as our model, natural logarithm y equal to natural logarithm alpha plus beta x, then that would imply running the following regression. So would be equal to linest, which is the regression. So what we're trying to do is estimate the beta on time, and the beta on time is the growth rate, and the y series is the series here, comma, and then we go back, and then the x series is time, so it's just one x or independent variable. And do we want a constant? Yes, we do. And do we want other statistics? Well, for the moment, let's say true. And what we can do is just return, and then to estimate the full regression, we have to set it up as an array of output. So Control Shift Enter, and what this provides us with is, in the first instance, this is the constant, right, which is relatively close to our 7.65, and this term here represents the growth rate over the entire period. Below, if we look at the linest function, we would see that we have an R squared, and we would have standard errors for this regression. Okay, and it would look as if both are statistically significant. So if these are this is the growth rate, or the beta, and this would be the constant, the log of the constant. So let's go back. So the constant and the beta would represent the growth rate. X is time. Okay, so let's save this, and let's copy the data that we have here. Copy, and just clean up a little bit. Paste. Let's take this set of rows out. So we'll delete, and let's run the regression again, but run not just one regression, but a series of regressions with the linest. So I'll do that in the next video.